Here are some of the concepts you need to be sure that you know in preparing for the test that's coming up next week. How do you determine a regions where function is increasing or decreasing? Remember, we've talked about it's very important to know the difference between function and derivative and those things. So to figure out where the function is increasing, remember that we've determined that that's where the first derivative is greater than 0. That tells us that the function is increasing. So what you need to do is to figure out where the first derivative is equal to 0. Then you want to do a sign line with that particular derivative. And then once you've done the sign line with that derivative, anywhere that the first derivative is greater than 0, it's increasing. If the first derivative is less than 0, it is decreasing. We also talked about critical points. Remember that to be a critical point, the first derivative has to equal 0 or the first derivative has to be undefined. One of those two states have to be there. F prime equals 0 is the one that you almost always remember. The fact that F prime is undefined, that's the one that students often forget. Inflection points, however, are a little bit different. Remember, inflection points are all about concavity. And inflection points are where the concavity changes. And that's a crucial piece to it there. To be an inflection point, the second derivative has to equal 0, or the second derivative is undefined, and at the same time the concavity changes. That just means that the sign changes on the second derivative from positive to negative or from negative to positive. You have to have both these things, the first derivative being 0 or undefined and the concavity changing for it to be an inflection point. To be a critical point, all you have to have is where the first derivative is 0 or undefined. That's the big difference between them. One's first derivative, one thing has to be true. Points of inflection are second derivative, and both things have to be true. Now, how do you determine if a critical point is a max or min, or neither, using the first derivative test? If you recall, we find out what the first derivative is. We set it equal to 0. After we do that, then we're going to do a sign line to determine the sign of the derivative in every place. And if the sign line looks like this, where it goes from positive to 0 to negative, then that tells us that this point here is a maximum, because the function is increasing, then it's 0, then it's decreasing. By the same token, if the sign line says it's negative and then it changes to positive, then that means that the function is decreasing, then the function is increasing. Therefore, that would mean that it is a minimum at that particular point. So that's how you would find that. This next question, how do you determine if a critical point is a max or min, or neither, using the second derivative test? This is one of those that you will not be required to use on a test, but it could be good information to have. And remember, if the first derivative is 0 and the second derivative is greater than 0, that means it's concave up. If both of those things are true, then it's going to be a minimum. If the first derivative is 0 and the second derivative is less than 0, that means it's concave down, so it's going to be a maximum. But again, you don't have to ever use the second derivative test. You can always use a sign line. And the sign line max and min is increasing to decreasing. Positive to negative is a max, negative to positive is a min. If there's not a sign change, if it's positive to positive or negative to negative, it's neither a max nor a min. Concavity. Remember, concavity is all about the second derivative. So to determine if it's concave up or down, you're going to find out whether the second derivative is equal to 0 or undefined. And then you're going to do, after that, you're going to do a sign line. So when we do our sign line of our second derivative, then if it's positive in an area, positive If the second derivative is positive, that means that it is concave up on that region. And if it is negative, that means it's concave down on that region. Mean value theorem. Mean value theorem, which we will write as MVT. Remember, for the mean value theorem, you have to have certain things that have to be true. F is continuous. And we've talked about continuous all year. That means that it's nice and smooth. If we're drawing it, we can draw it without picking up our pencil. The second thing is F has to be differentiable. Graphically, that means that it has no sharp turns in it. But also, remember, we've discussed this briefly, that really also means that the second derivative is defined. So if you've got those two scenarios where the function is continuous and the function is differentiable, then there's one more thing that you have to worry about. F of A, one endpoint, is not the same as the second endpoint. And remember, when you've got these three things, it's continuous, it's differentiable, and the endpoints are not the same, then there has to exist some number C so that the derivative of C is the function value at B minus the function value at A over B minus A. And we talked about this in real life terms using the police car. If a car is clocked at leaves a point and then drives a set distance away, let's say 5 miles away, and we find out that the time is 4 minutes to get there, then he's driven 5 minus 0 miles and 4 minus 0 minutes. So if we did that multiplication there and found out that it was 75 miles per hour, that was his average speed. Well, if his average speed is 75 miles an hour, then he had to have gone 75 at least one time during there. So that's what MVT says, that it has to exist somewhere between A and B to do those things. A corollary, very much a corollary to MVT, is Rolle's theorem. And remember, the only difference with Rolle's is that in Rolle's, F of A is equal to F of B. And if that's the case, that just simply means that there has to be a place between A and B such that the derivative is equal to 0. So the first two things still apply. Continuity still applies. Differentiability still applies. If you've got those two and they're equal, then the derivative is going to be equal to 0 somewhere. Remember, the difference between these rolls, if something rolls, is circular, so it looks like a 0. So Rolle's theorem, the derivative has to be equal to 0. Relative max and absolute max. Remember that to find relative max, relative is the highest in the area. So it doesn't have to be the overall highest. It could be high, but someplace else could be higher, but it's still a relative max. An absolute max is the highest. In order to have an absolute max, in order to be guaranteed to have an absolute max, then you have to have endpoints. So anytime you have endpoints, you're guaranteed to have an absolute max and an absolute min, an absolute highest point and an absolute lowest point. Now, some books will differ between if it's a relative max, if it's an absolute max, can it be a relative max? I would say that anything, if it's an absolute max, it's also a relative max. And we will leave it at that. You won't have any questions where you have to determine is it a relative only or an absolute only.